On to question 4 then. The situation is that there's a basketball player who scores 60% of their free throw shots, and in a particular game, they get the opportunity to make 6 free throws. So the question is, what assumptions must be made in order to regard this as a sequence of Bernoulli trials? Well, first of all, you need to know what the conditions are for a Bernoulli trial. Condition 1, a fixed number of repeated trials. There needs to be exactly 2 possible outcomes of each trial. The last 2 points then are very closely related. In fact, this point that the trials are independent could just be lumped in with the probability of success is constant. The fact that the trials are independent only means that a particular success or failure doesn't mean that the probability of success or failure in the future is going to be different. In other words, the probability of success is constant. But this statement here, the probability of success is constant, also includes other factors, and those other factors aren't necessarily just to do with prior success or failure. There could be any changing quality of your trial. So you can make all kinds of assumptions here, but first of all, just make note of the things that you're not actually assuming. So start off here, a fixed number of repeated trials. We're told that she gets exactly 6 free throws, so we don't need to make any assumptions about that. Secondly, exactly 2 possible outcomes of each trial. Now, you kind of need to be familiar with free throws for that, and there are just exactly 2 possible outcomes of each trial. It's no harm, though, to write down that success and failure are the only outcomes, because in other questions, they might not be the only outcomes, and that it will be an assumption that you have to make in order to complete a question on Bernoulli trials. The third point then, that the trials are independent. You could say things like the ability to free throw is not affected by prior trials, in that you could talk about all kind of psychological effect. For example, she doesn't get overconfident from getting a couple of free throws, or she doesn't get really nervous from missing a couple of free throws. Also, she could potentially get tired from the game, and that would hinder her ability. So there are a couple of assumptions you can make about her ability to free throw. Just another point you can make about the probability of success being constant is that the free throws are all taken from the same location, which of course is going to be true for free throws, but again, it might not be true for other scenarios you're going to be presented with in an exam. And of course, there are tens of other assumptions you could be making here. These are just a few examples to get you on the right track. Part B then is just to find the probability that she scores exactly 4 of the 6 shots. When it says based on those assumptions, what it really means is that you've now made these assumptions that qualify this as a Bernoulli trial, so that means you're allowed to use any equations related to Bernoulli trials, for example, this one right here. And that equation just came from right here on page 33 of the Formula and Tables book under binomial distribution. We're looking for the situation then that she scores exactly 4 of the 6 shots, which means that n is 6 and r is 4. So just go through the equation replacing everything. There's r is 4, n is 6, r is 4, r is 4, and n minus r here is 6 minus 4 is 2. P is the probability of success, which we're told is 60% or 0.6. Q is the probability of failure, which is 1 minus the probability of success, so you get 0.4. So this 6-4 here means 6 choose 4, so you put that in a calculator and you get 15. On a sharp calculator, it's the second function of number 5. I don't know what it is on a Casio. So the 0.6 to the power of 4 is 0.1296, and 0.4 squared is 0.16. Multiply everything together and you get 0.311. Part 2 then, you're told that she scores for the second time on the 5th shot, and you have to work out the probability of that. So the first point to make is that the question says she scores for the second time on the 5th shot. You're not looking for the probability that she scored at least twice by the 5th shot. It's that she scored for the second time on her 5th shot. So that means she scored exactly once in her first 4 shots. Secondly, she definitely scores for the second time on her 5th shot, which means that she has to make her 5th shot. So you have to find the probability of that as well. So first of all, we have to work out the probability that she scores exactly once in her first 4 shots. These are the 4 scenarios in which that happens. In one scenario, she makes the shot, then has 3 failures. She misses the first shot, gets the second, and misses the next 2. misses the first two, gets the third shot, misses the last one, or else misses the first three shots and gets the last shot. Those are all the different scenarios under which she'll make exactly one of her first four shots. Secondly, then, the probability that she makes her fifth shot is just this here, the probability of success. Remember that because this is a Bernoulli trial, any particular shot is independent of the others, so it's just the single probability of a success. So then the probability that both of these things happen, that's the probability of A with the intersection of B, is the probability of A times the probability of B given that A has happened. Now, since these are independent events, then the probability of B given that A has happened is just the probability of B, really. So then each of these four events here has exactly the same probability, so the probability of A happening is 4 times the probability of one of them happening, which is just going to be 0.4 by 0.4 by 0.4 by 0.6. And that's multiplied by the probability of B, which is just 0.6. And you follow that through and you get 0.092. It's also worth noting that instead of doing all of this stuff here, you could also treat that as a Bernoulli trial where n is 4 and r is 1, and you'll get exactly the same thing as this.